Okay, guys. I've got this lecture videotape for you guys so that you can watch it um, as part of your lecture, so you guys can do the next 3 pages in the homework. Um, we are talking about pages. We're looking at 15, 16, 17, 18, 19, and sorry, just through 19. So that was what, 15? Pages 15, 15, 16, 17, 18, and 19. And that's going to be your homework over the next 2 days. So I'm encouraging you guys to give it your best shot, and when you're stuck, come back and look at the video. It will be available on YouTube, even though we're showing it here in class. And don't give up on it. It's going to be a little challenging. If you guys have questions, you can send me messages on Edmodo, and I'll get back to you as soon as I can. But this should be enough information to get you guys through that. So we're going to start with a real quick review, and we started with position time graphs, so PT graphs, and if we have, that's a lovely graph right there. We had these different kinds of conditions that for our position time graph. Okay, we had one, and I'll try and do this in different colors here. We had one where we had constant 0 velocity. That means that our I'm sorry, not 0 velocity, constant 0 position. Oops. Constant 0 position. Okay, that means that, oh no, I did screw that up. Constant 0 velocity is what I'm looking for. So that it not only is our position staying the same, and we're going to mark that with a blue dot. Okay, not only is our position staying the same as we go across our graph. Okay, so let's say we go up, we have this position here, that our graph is going to look like this, that we have this constant, that our position, our position x versus t in seconds, we'll call this in meters. Okay, if we hold this position as time goes on, if our position doesn't change, then we get this horizontal line. Okay, so that was the earliest condition. That's the basic condition. The second one is if we have a changing position, if we have a changing position, then we have, then it can either be positive or negative. So in other words, we're either getting closer to the origin, and we'll get closer to the origin, and we'll call that red. Okay, or we will move away from the origin, and we will call that, I'll draw that in green as soon as I get my green pen at the ready, because it disappeared. Oh, there it is. Okay, so we have a changing position, but this is going to be a changing position with constant velocity that is not 0. All right, so if we have a changing position, with a positive velocity, that means, according to our left-handed slope, that we are going to be increasing, and we're going to go something like that with respect to time. And if we have a changing position but it is a negative, then it's going to look something more like that. Okay, and then we remember that the steepness, okay, it's at this point that we say the steepness, also known as slope, of the line means speed. Okay, so if we have more steep, more steep equals faster, less steep means slower. So you can see that the red is a bit steeper. Or here, let me give you a different one. Let's do that for our red. Okay, we can see that this red here, so we'll call this 1, and that's 2. That'll be 3, and this will be 4. We can see that line 1 is way steeper than 2, and so it's going to be faster. But 1 is also steeper than 3, and although 1 and 3 are in the opposite direction, 1 will be going faster than 3. All right, so let's get another one in here. Let's get a really fast. Okay, and we can see how line 5 in here, how line 5 is steeper than line 1. And even though line 5 is going in the backwards direction, it's going in the negative direction, it is still faster than 1. So steepness means speed. Okay. Then we have our third condition. And our third condition, now these two were both constant velocity. Third is if we have a non-constant velocity. And we came up with two versions of that. Okay, so we're gonna come down here, and this non-constant velocity on a position time. All right, so we're going to have a, well, let me get my, there's my good one, there's my cool one. Okay, so we're going to have a better axis. In fact, you know what, we're going to draw 4 of them. So we're going to do a 1, a 2, a 3, and a 4, and we're going to have 4 different little ones that we're going to draw in here. So just to all right, and then we're going to go, we're going to have a horizontal axis. Hopefully it's horizontal. Close enough. All right, so now we have two things. If we have velocity is positive, okay, but our acceleration is positive, then we're going to have a graph that increases in speed, and it's going to look like this. Yeah, then our next condition was if we had velocity was positive and acceleration was negative, that means we're going to start going up, but we're going to slow down because these are opposite to each other, and slowing down means that we're changing our position at a slower rate as we go that way, and our graph looks like that. Mind you, all of these are position versus time. Position, time, and position. time. All right, now our next situation was, we're going to do our negative velocities now. If our velocity was negative, meaning we're moving back towards the origin. Okay, so we're moving downward towards 0 here. There's our 0, our origin. And our acceleration is negative. Okay, we are going to get even faster in the negative direction. So we will start, and we'll look like that. It'll be a downward sloping curve because we'll be getting towards 0 faster as we go through time. And then finally, if we have a negative velocity and a positive acceleration, we're going to look like that. So these are for non-constant velocity situations on a position time graph. Okay, so now with that in mind, we need to move on to the next. So this is a review from last time. We now need to move on to the next kind of graph that we have, and that is the velocity time graph. So, need to get some stuff out of the way to finish this. All right. So now we are on to velocity. Velocity time graphs. Now these are very similar to, or we'll call them VT. These are very similar to acceleration time graphs, except all of these things are going to be stepped up ones. So we're going to have some straight lines, and just as how these had some conditions for their straight lines, we're going to have some similar conditions for velocity straight lines. So let's start with some conditions here. Okay, there is our, that's going to be our starting graph for velocity. Well, actually, we need to not draw our line there. And you'll see that because objects have a tendency to go forward and backward, it's going to be more convenient for us to do a horizontal line in the middle of our graph. So we have positive velocity up here, and we have negative velocity down here. So when we're going forward, we're up in this direction. When we're going backward, we're in this direction. And this is still time. Okay, I like sharpened pencils when I'm doing this. Okay, so let's come back to our conditions. Remember these conditions where we had constant zero velocity, changing position, and non-constant velocity? Well, we're going to have similar stuff down here. Let's do these same conditions. So if we had a constant zero velocity, what was that going to look like? Well, we colored in blue before, so we're going to color in blue here. Okay, so it's going to be blue for us. If it's a constant zero velocity, that means our v is going to be at 0, and it is going to be traveling right along there, because this is where velocity equals 0. Constant zero velocity, velocity is always at 0. Okay. Now, our step 2 was a constant positive or negative velocity, positive, negative velocity. And this we colored in green and red. Well, I'm just going to stick with red for this one because I'm going to save green for the next. This is going to be red for both of them. So think about this. If we have a constant positive velocity, here's our velocity. Above 0 is positive. And so we will have, and so constant is going to be another horizontal line, but in this case it's going to be above 0, or negative will be below 0. Okay, so this would be some v naught, which would be positive, and this would be some v naught, which would be negative. In fact, I don't want that positive there, I want that positive over here. And so this would be a negative v naught. So both of these, but they're both staying constant over time. If we're not changing over time, then our lines are going to stay horizontal because we have a constant velocity. Our third condition was a non-constant velocity. Okay, this means if we have a non-constant velocity, that means we're going to have a delta v, and whenever we have a delta v, this implies that we have an acceleration. Okay, we're going to draw this one in green, but we can still have a plus or a minus. This can be a plus or a minus, a positive or negative line. But if we're changing over time, okay, then the slope of the line becomes like that. This is going to be our positive, our increasing velocity. Okay, and this is going to be a decreasing that is a decreasing velocity. Now, take a look at this. This increasing velocity, remember that the value of the velocity, and the value here is given by, maybe I've got another fancy pen here I can work this out with. I think that'll work. Nope, not yet. The value of the velocity at any given time is given by the horizontal line. So let's look at this horizontal line right here. Oh, that didn't leave any marks. That's not. There we go. Let's try this again. Okay, so notice that right here, right there, okay, this value is a positive value, positive velocity value at this point for an increasing velocity. This guy over here is a decreasing velocity. It's got a negative slope. But at this particular moment in time, right here, it has a positive velocity value. That just means that it's going from a plus number down to a minus number. So this could be like a plus 5 meters per second, and down here could be like a minus 3 meters per second. And that would be a decreasing velocity. And this moment right here would be, say, plus 1 meter per second. So as it travels, it is decreasing. And down here, this could be, say, like a negative 7 meters per second, and we're increasing. Right there where it crosses, those are both 0 meters per second. Okay? But this would then become positive, and up here, it's like this would still be that 1 meter per second at that point. And then up here we could be, you know, up here like 5 meters per second again. So we go from negative 7 up to 5. So this would be an increasing velocity. That would be a decreasing velocity. But the horizontal value is what the velocity equals in any particular time for a velocity time graph. Okay. That being said, there are some interesting things that we can do with our velocity time graphs. Okay, because, so it is time to flip the page. Because on a velocity time graph, on a velocity time graph, let's say for 3 seconds, okay, we are traveling, we're taking a walk. Okay, we're taking a walk across campus. And if you guys have ever seen me walk across campus, I have like the furthest classroom from civilization here. I'm sure you guys know that because you come here every single day and you have to go all the way out to S16 to get what you need to get, or to come to class. Or say you have to go to your locker, and you have to go all the way back to your locker, then all the way back out to S16. Well, I got stuff to do during the day, and so if I'm out on campus, I'm moving. And I tend to walk with a velocity of about 2 meters per second. I'm hauling. I don't have time to waste. And if I'm going to go somewhere, I'm in a hurry to do it. And if I do this for 10 seconds, if I travel at this 2 meters per second, constant velocity, for about 10 seconds, here's 10 seconds. Okay, how far did I go? What is my displacement? And remember that delta x, our displacement, equals our velocity times our time. Well, we know the velocity is going to be 2 meters per second, and our time would be 10 seconds. So our total displacement would be 20 meters, particularly if I'm just going in a straight line. Okay. But look at this, 2 meters times 10 seconds. Well, that looks like 2 meters times 10 seconds. Well, what is this shape that I have here? Okay, I've got this. What is the shape I have here? Sure looks like a rectangle to me. Okay, and the area of a rectangle equals base times height. But in this case, our base times height equals our time times our velocity. Well, v times t is the same thing as our displacement that we have over here. So this is really a remarkable coincidence here. This is a very profound idea that the area under the graph of a velocity time graph is equal to the displacement. This is a pretty important idea, and it doesn't just work with rectangles. So let's come up with a different let's do a different one, and let's say instead of when I first get started walking, you don't start at 2 meters per second, you start at 0, and it takes me a bit of time to get it to top speed. So let's say that is the path I take. Let's just do I do this dotted line path. So I start at 0, and I get a little bit faster. Okay, all the way up to that 10 seconds. Well, how much distance did I travel? Because I started at 0 and I finished at 2 meters per second. Okay, I can't just draw the rectangle. In this case, we have a triangle. And the area of a triangle is one half of the base times the height, or in this case, our displacement then is going to equal delta x is going to equal 1/2 times our v naught times our time, and that would be my displacement. So in this case, it's going to be 1/2 times 2 times 2 times 10, which would wind up being, so 1/2 times, I'm sorry, this is v final, 1/2 2 meters per second times 10 seconds, and that would end up being 10 meters. Well, look at that. 10 meters is going to be half of the rectangle, and that's what you get when you cut a rectangle into triangles. Okay. This also works even further. We can even do this also works with like a trapezoid. So let's do a real quick one like that. So we have, let's say I'm already walking at a speed at 1 meter per second. I'm just strolling across campus, and then I need to get in 10 seconds to, I realize I forgot something, and I start speeding up. So now I have, okay, v t 10 seconds, and I speed up to 2 meters per second, but I was already traveling at 1 meter per second. So that we can do this in one of two ways. We can find the area of that rectangle, okay, and the area of the triangle, okay, and add them together. So this would be 1 meter per second times 10 seconds equals 10 meters. Or up here, this would be 1/2 times, and this one, what is this height right here? That's going to be 1 meter per second, or we would get that by a 2 minus 2 meters per second minus 1 meter per second, because that would be v final minus v initial, also known as delta v. That's our change in our velocity. Okay, and then our time would still be 10 seconds. This would wind up being 1 meter per second times 10 meters. 1/2 times 1 times 10 equals 5 meters, and this total area would then become 15 meters per second. And that's if I started at 1 meter per second, sped up to 2 over that 10 seconds. Okay, or the other way we can do it is, if you remember the area for a trapezoid, the trapezoid it's the average of the bases, so it's going to be base 1 times base 2. I'm sorry, base 1 plus base 2. Base 1 plus base 2 over 2, because that's the average of the bases. It's this one plus that one divided by 2, times the height, which in this case is this distance here. But if we're going to put that back into our terms, this is going to be v final plus v initial over 2 divided by our height, which would wind up being, our velocity final was 2 meters per second plus 1 meter per second was our v initial over 2 times our height, and our height here is just our time, which is going to be 10 seconds. See, I can turn it around like this, and here's a trapezoid, base 1, base 2. Now it looks like a height, right? So, okay, this becomes 3 meters per second over 2 times 10 seconds, and I'll just do a little math here. That's 5, and that's 1. 3 times 5 equals 15 meters. And that should be about what you need for the next few pages. All right, so feel free to go back and forth. I'm going to leave these notes here so you guys can take a look at them if you want to. These will be up here with your substitute. So have a good rest of the week, guys, and I'll see you back here on Monday.